The next part of our conversation about gases and their property and behavior is a little bit further down on our list of learning objectives, and that would be to use the things we've talked about so far and perform stoichiometric calculations to relate the mass of a reactant to the mass, moles, or volume of some other product. So it's a little bit of a different application of stoichiometry, but it's completely connected to things we've seen before, an interesting application. When we're talking about this type of stoichiometry, what we have to convey is how you get from the amount of one reactant, whether it's grams or volume, to the amount of a product. Grams or volume, actually it could be an amount of another reactant, but any two items or species in a reaction. And this is a variation of stoichiometry we've seen before, where we always have to relate the moles of one item to the other. And so we can relate volumes or moles of any particular item or gases in a reaction mixture, because the ratio of volume to moles is going to be a constant anyway. So we're still going to have to go back to ratios of moles in the components of a balanced equation. So as always, check to make sure that you've begun with that. Let's talk about that in some context and some details. So why does this work? Well, we're going to talk about this in terms of Avogadro's law for a moment, to think about the fact that the volume is proportional to the number of moles. The ratio of volume to moles is a constant, or volume equals a constant times the number of moles, either one. And the ratio of the volume and number of moles of one substance, or in one set of conditions, will be the same as the volume to the number of moles at a second set of conditions. And these all, of course, have to assume constant temperature and pressure. So if you're doing a particular reaction and discussing the comings and goings of different aspects of the parts to it, it's all in the same place with the same temperature and pressure. So this is going to be applicable. And here's an interesting diagram that represents this idea. So if you're going to take hydrogen and nitrogen to combine them and make ammonia, it takes 3 molecules of nitrogen, if you look at the left box, combined with 1 molecule of nitrogen to make 2 molecules of ammonia. Now we've talked about how the coefficients in a balanced equation are used, and it can be used to mean molecules, but it can also be moles. In other words, 3 moles of hydrogen react with 1 mole of nitrogen to make 2 moles of ammonia. That's another way of interpreting those coefficients. But the third way now, realizing that volume and moles are proportional to each other, directly related by a constant, then 3 volumes of the hydrogen could be related to combined with 1 volume of the nitrogen to give us 2 volumes of the ammonia. Interesting way of thinking about it. Okay, so here's an example of a gas phase reaction, all the components are gases, that could use that kind of relationship. So acetylene, also known as C2H2 there, or ethylene, or ethine actually, can be generated by reaction of calcium carbide with water. And we can calculate the amount of oxygen in liters required for complete combustion of this acetylene. I'm going to draw out the structure for you, just so you know what it is we're talking about. 2 carbons and 2 hydrogens in that kind of arrangement, but that means there's a triple bond in there. And how much oxygen would be needed for complete combustion of this acetylene, assuming we have the same pressure and temperature. In other words, it's all in the same reaction mixture, so the pressure and temperature haven't gone anywhere. So if you know the volume of the acetylene, I want to call it by another name, it's also called ethine, then you should know the ratio of the volumes of the other gases that will be used. In other words, the number of moles corresponds to the volume. And so the ratio of the moles will equal to the ratio of the volumes. Given 2.5 liters of C2H2, we're trying to figure out the amount of oxygen needed. And so 5 volumes, or we'll say moles in this case, oxygen will correspond to 2 moles of C2H2, and it's going to be in the exact same proportion as the volumes. And so all you have to do is work out the math here, and you'll have an answer. So put your trusty calculator to work. 2.5 times 5 sounds like a number we can do. That will give you 12.5, and you divide that by 2. And if your math is working for you, that should be 6.25, same thing, same unit now, liters of oxygen required. So it's a very simple relationship once you know how to use it. Now, we won't always use it that way, but sometimes we will. And so the other kind of way of doing this is going to be with grams. So the next example will go that direction. Uh-oh, I just put something in here I didn't intend. So let me change that. Now, that becomes readable. So the other way of writing this that would have been perhaps clearer for you is if I had said 2.5 liters of C2H2 and 5 liters of oxygen reacts with 2 liters of C2H2. Mathematically, we've got the same thing. The ratio of moles is going to be the same as the ratio of volumes or liters, and you'll get the same answer. Now, another example. Sodium azide is what's used in airbags in cars, and it's used to produce nitrogen gas, which is otherwise harmless, and some sodium left over. The main issues with that are the impact and the heat that are generated. Hopefully you don't ever have to encounter that firsthand. So what we can do is, this is a gas law stoichiometry question, because we can evaluate and determine how many liters of nitrogen might be generated at a particular pressure and temperature by the decomposition of 45 grams of sodium azide. So what will we have to do? We have what things provided. This will be the pressure. This will be the temperature. Oh, but we need to convert to Kelvin, right? So add 273 to that. Well, let's just do it right here where you can see it. We'll add 273 to make sure we're in Kelvin. Always the way to go in gas laws. So that's 303 Kelvin is the temperature. We'll have to determine how many moles this is, so we'll need a molar mass. And from that, we can determine the number of liters of the sodium azide and also the number of liters of nitrogen. All right, ready, set, go. On the next slide. So the number of moles of nitrogen produced. Well, let's see. We're going to have to figure that out, or then we can go about both directions. Starting with the amount that you're provided of the sodium azide is a good place to go. 45 grams of sodium azide. Well, then we'll have to multiply it times the molar mass. So here we go. And if you add them up, you'll find out that it's 65 grams per mole. And that allows us to cancel out the grams of sodium azide. But that doesn't get us enough answers because we want to know how many moles of nitrogen. So we'll look at the balanced equation and figure out the relationship between the two. And that means that we have 3 moles of nitrogen for 2 moles of sodium azide. And if you're paying attention, things are canceling out along the way, such as grams of sodium azide, moles of sodium azide. And this tells us how many moles of nitrogen would correspond to that amount of sodium azide. Then we need to know the volume, because we want to know how big that airbag is going to get. And so given a number of moles, that's N, right? And on the previous slide, we had pressure and temperature. Then we only have to rearrange the ideal gas law to come up with the volume. So volume will be nRT over P. N is right there. So there's your 1.04 moles. R is the same thing it always is, but we have more sig figs than sometimes you see in this particular view. And then the temperature is in Kelvin. They've added the 0.15 in and rounded it off to 2 in this case. And the pressure was given as 1.15 atmospheres. This becomes a math exercise. Be sure that the units make sense to you. Double check that the moles have canceled, the Kelvin should cancel, the atmosphere cancels, and all that's left is liters, which is what you are hoping to see when you are doing a calculation for volume. 22.5 liters, it's a number. Is that big enough to inflate an airbag? Apparently it's a good number for an airbag. All right, let's try something else. If we're going to do stoichiometric relationships with gases, what about the volume of CO2 produced at 37 Celsius and 1 atmosphere if a certain amount of glucose is used up in the reaction? Here's our glucose combustion reaction. And what will we have to do to come up with that? We want to know the volume of CO2, and we're always going to have to go between reactants and products. In this case, the product is going to be the CO2. The reactant is the glucose, which is C6H12O6. You'll recognize that eventually, I suppose. The temperature is given but let's put that in Kelvin to make sure we're right. Pressure is there. Got to write the numbers correctly. 273 added to 37, 273. Put those together, and I'm going to add up someplace here, and we'll get, looks like 310, right? 310 Kelvin. And that will give us temperature, pressure. We're going to be able to calculate the number of moles of carbon dioxide based on the number of moles of glucose. So we're going to calculate the amount of moles of the CO2 based on the grams of glucose. Okay, so what will we do? The grams of glucose give us moles of glucose. Relate that from the balanced equation to moles of CO2, and from that calculate the volume. So 5.6 grams of glucose, and if you haven't remembered it, it turns out that it's 180 grams per mole for glucose, and that should cancel out grams of glucose. Looking at the stoichiometric relationship, there are 6 moles of CO2 in this reaction for each mole of glucose, and so that allows us to cancel out moles of glucose, which is always a good thing. Oh, there go the cancels. All right, they were there already. And that tells us the number of moles of CO2. Given the number of moles of CO2, which is just a mathematical exercise here, then we can use that to determine its volume. We have N, we have pressure, we have temperature. And we said that was 310 Kelvin. And this is just an ideal gas law rearranged. So the volume is going to be nRT over P. Get used to this equation. It's not so bad. And put in the numbers. Check it out. Make sure it looks right, because hopefully things are going to cancel. The moles cancel. The atmosphere cancels. The Kelvin cancels. And all that remains is liters. That's what we're hoping for a volume. If we've set it up correctly, all but the intended units will cancel. And it's a number. It's 4.76 liters. It's a mathematical exercise, but this is an example of how we do stoichiometry with gases. In other words, we have 2 steps. First of all, we can determine how many moles of the product are needed based on stoichiometry and mole ratios. And the moles of the product then is determined, can allow us to determine the amount of product in grams or volume using the gas law. The ideal gas law will allow, is useful here in getting that value. Okay, I hope you find this helpful. Good luck on your homework. You can ask me more questions as needed. Send me an email if that helps. Otherwise, I'll see you in class.